Good afternoon, ladies and gentlemen. My name is Sofia Sassone, and the Meteorite Team 2, composed of myself, Annie Lee, Kiera, Aston, and Tanya, Vijay, presents to you our research into determining the origin of meteorites through chemical analysis of isotopic composition. Isotopic analysis of meteorite samples has been vital in determining their ages, origins, and location in the solar system. We determined that Martian samples' higher ratio of oxygen 17 and 18 and excess xenon 129 helped identify their parent body. Lunar samples have almost identical oxygen isotope ratios to those on Earth, and differentiated meteorites and chondrites reveal distinct isotopic reservoirs, possibly isolated by proto-Jupiter. This approach also aids in dating iron meteorites with aluminum-26 and linking ordinary chondrites to S-type asteroids. Our goal was to determine how different isotopes can be used to determine the origin of meteorites, and what that analysis can tell us about the solar system. Isotopes are variations in elements that retain the same number of protons but have different quantities of neutrons, affecting these isotopes' weights and stability. They're measured using secondary ion mass spectrometry, where reflected ions from a sample are exposed to an electrical or magnetic field. Many of these isotopes, such as those of oxygen 17 and 18, undergo fractionation, where they get separated between different states of matter. The ratio of the separation in different physical processes on a body can be graphed. That, using data from the Earth, is known as the terrestrial fractionation line. Many planets have their own sort of signature of this isotopic ratio, which can then be used to identify whether a meteorite came from that planetary body. The protoplanetary disk, a dense envelope of gas and dust around a newly formed star, is where many early planets began to form, and thus began developing their own isotopic identifiers. From these bodies originate meteorites, some of which are known as chondrites, or stony meteorites that come from asteroids and contain small chondrules, which are spherical inclusions that contain material from the creation of the solar system.
Due to the wide range of our topic, we decided to focus on a select few isotopes and places of origin. We started by determining the places of origin that a majority of meteorites originated from: Mars, the Moon, and the protoplanetary disk. Then we determined isotopes that helped differentiate meteorites from those three places. These isotopes were aluminum-26, chromium-54, xenon-129, oxygen-17, and oxygen-18. All five of these isotopes provide valuable insight in differentiating unknown meteorite samples using isotopic ratios, general trends in the type of meteorite group, and knowledge of the composition of the parent body. We reference scientific papers that use methods like laser fluorination and secondary ion mass spectrometry to determine isotopic percentages in unknown meteorite samples. Then, by comparing the results to known origins of other meteorites or parent bodies, the origins of the unknown meteorites can be verified.
In our research, we found distinct variations in the concentrations of certain isotopes in meteorites from different parent bodies. Martian meteorites have been found to have a significantly higher concentration of oxygen-17 and oxygen-18 than other meteorites or terrestrial rocks. This graph shows the terrestrial fractionation line along with the Martian fractionation line, and the relative difference in concentration of oxygen isotopes in parts per thousand compared to a standard. So, as you can see, Martian meteorites have a significantly higher concentration of oxygen-17, making them distinct. Martian meteorites have also been found to have a higher concentration of xenon-129 than other meteorites and rocks. The oxygen-17, oxygen-18 ratios have also been observed for lunar meteorites. The ratios found in lunar rocks have very little deviation from the terrestrial fractionation line. This matches the data found from lunar samples collected during the Apollo missions.
This graph displays the chromium-54 and oxygen-17 deviations from a standard terrestrial mass fractional line. By doing so, it shows a clear difference between differentiated meteorites and carbonaceous chondrites. We can see most of the carbonaceous chondrites, with a few differentiated meteorites in there, plotted along the right side of the graph, and a majority of the differentiated meteorites clustered at the left side. Furthermore, the isotopic ratios of the Moon, Mars, and Earth are located among the left side cluster. From this graph, we can conclude that carbonaceous chondrites are isotopically distinct from other chondrites, and the majority of differentiated meteorites are isotopically similar to non-carbonaceous chondrites. One factor that could explain this difference is the groups of meteorites forming at different places on the protoplanetary disk. As the disk grew, variations within the disk would have been reflected on the meteorites that formed there, leading to the trends observed in the graph.
As mentioned earlier, our research focused primarily on 5 isotopes: chromium-54, xenon-129,
oxygen-17, oxygen-18, and aluminum-26. Firstly, directing our research focus to carbonaceous chondrites. Chromium-54 isotopes found in carbonaceous chondrites proved useful in determining the origin of certain meteorites. For example, scientists studying the Orgyle and Murchison carbonaceous chondrites, which fell in France and Australia respectively, determined that the chromium-54 found within these meteorites originated from spinel, which are grains produced by supernovae that are known to be smaller than 100 nanometers. Given that refractory inclusions, like CAIs, tend to lack chromium, they cannot be the source of the chromium-54, thus suggesting that parts of these and other similar meteorites originated from supernova spinel. Calcium-aluminum-rich inclusions are rarely found in ordinary chondrites, but are found in much greater frequency in carbonaceous chondrites, which are accreted farther from the sun, despite the fact that CAIs form near the protosun while exposed to radiation from solar particles. Carbonaceous chondrites also have more refractory elements, such as calcium, aluminum, and titanium. The leading hypothesis for these trends is that elements within the refractory inclusions were transported from the region in the protosolar disk where they were formed by disk winds, and were then prevented from spiraling back into the inner solar system by proto-Jupiter. Now turning to our research into Martian meteorites. Xenon-129 is found in excess in Martian atmosphere and soil, much more so than in Earth's atmosphere. Traces of Xenon-129 found in gas bubbles in Martian meteorites suggest Martian origin. Furthermore, oxygen-17 and oxygen-18 are found in consistent ratios in all studied Martian meteorites, creating a dataset to which isotopic composition of other meteorites can be compared against. Looking beyond gaseous or planetary parent bodies, chemical analysis of isotopic composition can also be applied to asteroid parent bodies. The Hayabusa 2 mission to asteroid Itokawa serves as an example. The ratio of oxygen-17 and oxygen-18 in Itokawa's pockets of olivine, orthoperoxine, and plagioclase indicates that the oxygen fractionated while in dynamic equilibrium between two physical states. This process is also known as thermal metamorphism. Given that this behavior was also observed in ordinary chondrites, it was determined that ordinary chondrites originated from S-type asteroids. Isotopic composition analysis can also be used in the context of dating. Aluminum-26 has a half-life of 717,000 years and can only form in hot environments, such as supernova explosions, suggesting that it was abundant in the protosolar disk. It is also produced due to spallation of silicon. Once entering the Earth's atmosphere, its production drastically decreases since the atmosphere erodes surface silicon. This allows aluminum-26 to be used for dating meteorites upon their entry into Earth. SEAS has impacted us all in unique ways. SEAS gave me the opportunity to explore a niche aspect of space science, equipped with the tools and skills to conduct research and collaborate with esteemed peers and professionals, further solidifying my interest in space exploration.
SEAS allowed me to dive deep into the mysteries of the universe and deepen my love for STEM, of which I will cherish in my future pursuits.
Thanks to SEAS, I have acquired invaluable insight into meteoritics and have gained a greater appreciation for research scientists. Collaborating with like-minded peers has been an incredible opportunity. This program has certainly reinforced my desire to pursue a career in STEM.
I am very grateful to SEAS for giving me the opportunity to work with incredible people from across the country and for letting me do research. It has let me explore my passion for STEM in a fun and engaging way, and I'll definitely treasure this experience.
Our SEAS experience was filled with many highlights, including having the opportunity to conduct research and learn new information, as well as to meet new people and learn from esteemed guest speakers and mentors. We also faced some challenges when it came to digesting scientific journals, compiling information, and understanding new concepts regarding the formation of meteorites and of our solar system. However, we believe that we have come out of the SEAS experience as stronger and more passionate STEM students.
We would like to thank Margaret Baggio, Selena Miller, University of Texas at Austin Space Center for Research, Suzanne Foxworth, and Maritza Montoya, all the NASA Ares speakers, and all the SEAS speakers. Thank you.